in this video we're going to look at two industrial processes that use Le Chatelier's principle in order to decide what conditions to run their reactions at. Okay, so the first one we're going to look at is the Haber process, which we looked at a little bit in the last video as one of our examples, looking at Le Chatelier's principle, and at the end we'll come on to the contact process as well. Okay, so the Haber process looks at the manufacture of ammonia, which is NH3. Okay, so this is our reaction that we came out with. From our last video we know this is an exothermic reaction, and also an increase in pressure would lead to an increase in the forward reaction. Okay, as there are more molecules on the right hand side, so there are 4 molecules here, and there are only 2 molecules on your right hand side. Okay, so increase in pressure would favour the forward reaction more than the reverse reaction. Okay, in some of these slides they don't have an arrow that goes in both ways, but just for these, maybe assume that the arrow does go in both ways. Okay, so according to Le Chatelier's principle, a high pressure and low temperature are the best conditions to give a maximum yield of ammonia. That is because this is an exothermic reaction, and we know that if we decrease our temperature, our yield increases for exothermic reactions. Okay, so our yield of ammonia would increase if we lowered the pressure, and similarly if we increased the pressure, then that would favour the forward reaction as well. So you would think that in industry that they would go for high pressure, low temperature situation. Okay, in practice that isn't really what happens. Okay, this is kind of a diagram of how ammonia is made in industry. When we look at industrial chemistry, we will look at the workings of this system a little bit more. For now we're just looking purely at the reaction, okay, and the role of Le Chatelier's principle in deciding upon the conditions necessary for the reaction to take place. Okay, so the reactions that it actually takes place at is at 200 atmospheres. This temperature, 380 to 450. You can up that a little bit to between 500. Okay, this pen isn't really working. 500 to maybe 650 degrees Celsius. Okay, these figures here aren't wrong, but just in some leave insert marking schemes I have seen that they have only accepted answers of above 500 degrees Celsius. Okay, and it also takes place with an iron catalyst as well. Okay, so if you were just looking purely at the equilibrium theory and we're trying to decide on your temperatures, you would think it would be at a low temperature because it's an exothermic reaction, and a high pressure, okay, because the forward reaction produces less number of molecules. Okay, kinetic theory then favours a high temperature, a high pressure and a catalyst. Okay, high temperature because you're giving the molecules more energy. Okay, so they're moving faster, they have more energy associated with them, so there's going to be more effective collisions between them, and more frequent collisions as well. High pressure, again more frequent collisions, and catalyst then would lower your activation energy. Okay, so they're things that you would see when we're looking at our rate of reaction chapter. Okay, what really happens is that they come up with a compromised temperature. So what favours the equilibrium theory, what kind of satisfies the equilibrium theory, what also satisfies the kinetic theory. You're not going to have a situation where you favour both 100%, so they come to a compromise. They come to conditions that go along with both of them a little bit and give them a good result that is viable both for their production and also economically. Okay, so in industrial chemistry, a lot of what drives it is the cost of things. So the cost of having something at a low temperature and high pressure is very high, and similarly at having at a high temperature, high pressure anti-catalyst, that also costs a lot of money. So people at the end of the day want to make money, and they're not going to do that with those at those conditions. Okay, so what actually happens is that you have a pressure of 200 atmospheres, you have a temperature of between 500 and 650 degrees Celsius, and you do have an ion catalyst to lower the activation energy. So they are the compromised conditions that they come up with. Okay, so the ideal conditions for the Haber process. Okay, so a compromised temperature of 500 to 650 degrees Celsius. Equilibrium is reached quickly, although the yield is lower. Okay, so if that temperature was even lower, okay, your yield would be greater. Okay, a compromised pressure of 200 atmospheres. Okay, higher pressures would give higher yields. Okay, so that pressure could be higher and you would get more from it, but the cost of it would be too great. Okay, and a catalyst of finely divided iron is used. Okay, it's important to note that a catalyst has no effect on the position of the equilibrium. Okay, so it doesn't mean that it's shifted to the left or to the right or anything like that. It does mean that that equilibrium, that dynamic equilibrium state, or that dynamic equilibrium that we are looking for is reached faster. Okay, but it has no effect on the point of equilibrium. Okay, it reaches equilibrium quicker, but it doesn't have any effect on the actual position of equilibrium. Okay, so reversible reactions used in industry. So the production of ammonia is one. Ammonia does decompose again. Okay, so it goes from nitrogen and hydrogen to ammonia, and it also goes from ammonia back down to nitrogen and hydrogen. Sulfuric acid is manufactured by oxidizing sulfur dioxide to sulfur trioxide. Okay, so you have SO2 and O2, and you make SO3 with that. Okay, and then from there you have H2O and SO3, and you would produce sulfuric acid from that. Okay. Okay, so these are some of the uses of ammonia. So making fertilizers. Okay, so for farmers, ammonia is very important for them to fertilize their land, to grow their crops, to feed their animals. Okay, and ammonium nitrate and ammonium sulfate are two of the fertilizers they use, and also you can make nitric acid. Okay, so it can be oxidized to form nitric acid. Okay, and that nitric acid then again can go on to be used to make fertilizers. Okay, so ammonium nitrate. So actually, that's it up here. This is the nitric acid. Okay, explosives and polyamide polymers. So nylon, basically, that your clothes are made out of as well. This is your second example then. This is the contact process. Okay, the manufacture of sulfuric acid by the contact process. Okay, so we saw this just a few minutes ago. Okay, so according to de Chatelier's principle, a high pressure again and low temperature, because this forward reaction is exothermic. And this side we have three molecules. On this side we only have two. So you would think that high pressure, low temperature were the best conditions to give a maximum yield of sulfur trioxide. Okay, in practice the reaction is actually carried out at a pressure of 1 atmosphere and a temperature of 450 degrees Celsius. Okay, with the vanadium pentoxide catalyst. Okay, sulfuric acid is used in the production of paints, detergents, plastics, fibres, car batteries and plastics, and about 156 million tonnes of it are used each year. Okay, it is produced by the contact process, okay, by the name of it. Alright, the name suggests that it's two things in close contact with each other. In this case, it's two gases need to be in close contact with each other. The sulfur dioxide gas obtained by burning sulfur in air and oxygen pass over a catalyst, this vanadium pentoxide catalyst there. Okay, that passes over it. Okay, in order for this process to occur, the gases need to be in close contact with each other. Okay, that close contact happens over the catalyst. Okay, the sulfuric acid is made by dissolving the sulfur trioxide formed in water. Okay, platinum could also be used as a catalyst as well, but unfortunately it's easily poisoned, so again it wouldn't be the best thing economically for the process, so this vanadium pentoxide is a much better option for them. Okay, there are 3 molecules on the left hand side and 2 on the right, so high yield is favoured under high pressure. Once again, this isn't economically viable, so it's conducted under atmospheric pressure. Okay, so unlike the Haber process where they did actually have a pressure of 200 atmospheres, this one is just undertaken at atmospheric pressure. The forward reaction is exothermic, therefore high yield is given at low temperatures, and a temperature of about 450 degrees Celsius is used. Okay, lower temperatures cause a slow rate. Okay, so again, not economically viable. Okay, at a lower temperature at an even lower temperature.